What the hell, though? All right. Well, this didn't change anything, which I guess it was weird to expect that it would. I'm just gonna check. Yeah, I don't know. Let's go on and see if something changes. Hello,
Fair.
everybody. How are y'all doing? We are live. You know, that was an unnecessary thing to say. Of course, we're live. We're here. I'm here with Leandro, and this is part 2 of making a gravity-based JSFX. I'm seeing on my panel here that we are uploading at quite a low speed. So please let us know if the video is choppy and weird, and if anything is, less than optimal, which I'm actually seeing. It looks okay, and it sounds more or less okay, but not great. So yeah, please let us know if you have trouble or if we're having trouble, and I'm gonna pass it to Leandro. How's it going, Leandro?
Hey, Arya. Great to be here. Thanks for having me over again. And I'm looking forward to actually listening to this effect. I think we'll be able to have something that will work today. So I'm excited about that.
Yes, same here. So I guess we can start with a little bit of recap in case you've not been with us last episode, but obviously watched that last episode because the conception of, or the conceptualization of this delay is not like your typical delay, and we can also call it ping pong delay because there's already a thing called ping pong delay, but this is not a ping pong delay. This is a ball drop delay. So Leandro.
Yeah. And people on the chat are saying that the stream looks
Oh,
good. So
perfect.
that's good news. And hello, Bo and Dominique and Ryuzma81. Great to have you
Yes,
here.
thanks for being here. I'm glad to hear that it's working okay. Since we're just streaming really text and faces, it's probably all right. And okay, so Leandro, since you're the guru, how about I try to like make sense of what we've written so far, and then you can fact check me.
Yeah, before you even explain what the code is doing, you should explain what the effect is supposed to do.
Okay, sure. So basically what this effect is, and I'll give you a shorter version than I gave you last time, is, I guess, yeah, it's like a gravity-based delay. So if you imagine as the original sound that the delay listens to as a ball, the ball drops and hits the floor and then bounces off the floor and loses some energy and then hits the floor again and again and again. And each time it hits the floor, it's at a lower velocity. Therefore, it travels up, and it travels up for a shorter distance and hits the ground at a smaller time period. So it will sound like if you drop a ping pong, it sounds like this.
I don't know if the stream hears anything, but I don't.
Oh, the stream does, and let me just make sure that you are hearing that. I think the stream heard that, right, y'all? Oh yeah, the reason you're not hearing that is now no longer a reason. Okay, so let's just play it one more time. So I drop a ping pong ball on the floor and it goes. Like that. So
Great. Did you re-record this?
no.
It seems clearer.
I just EQ'd it very, very simply because you can still hear yourself. You're saying something in the back like it works or something. Yeah.
Okay.
So
And gave you a piece of homework last time, which was to record this again with a specific height, like 1 meter, so we would know that our formula is working or not.
And I forgot. What do you say? Should I record that now or?
No.
Okay.
We can just move on with what we had,
Okay.
which is this recording, and we don't know exactly the height, but if we have a slider for height, so if we can get the first one aligned, then the rest should align,
Right.
if we got this right.
Yeah, sorry about that. I guess I will do that as my, then I can do that as like a fact check. So once we have this written, I will record it from 1 meter, and I will, I'll just choose, or what do you call it? Yeah, I'll just re-record that, and then I'll check it against our plugin, so to speak.
Yeah, it's no big deal. In fact, the end goal is for this to be musical. I don't even care too much if it will be physically accurate.
Right, same.
And as long as we hear something that we like, it's fine. But having a ball drop of 1 meter could be nice, just for making sure that maybe we are going to hit the target with the formulas. Yeah. But whatever.
And then we...
So do you want to dive into the code?
I just want to show this too. We like put markers on the transients of these. So if the first ball hits at 0, this is kind of the time it takes for the subsequent like drops to occur. So by the end, you're going to values of 100th of a second. So therefore, you are it's basically oscillating. It would have a perceivable fundamental pitch that we can discern, which would be around, let's see here. Like by the end, it could be around like 50 hertz or something, which is interesting. And since we have control over the physics in our effects, we can definitely also add that to one of our, really like see how much control we can provide over that parameter. So we got some ideas here. This was my homework, which I fucked up and forgot. Sorry about that. So yeah, on to the code. So far, pretty simple, not too many lines. We have the first slider, which is the height from which you drop the ball of sound. And then we have a gravity amount in G. So 1 G is 9.8 meters per second. Actually, 9.8 meters per second squared, right? Because it's the acceleration of falling objects on Earth gravity. And then we thought, hey, it'd be cool if we could also drop a ball on the moon gravity or on Jupiter, right? And those will fall at much faster or much slower velocities. But anywho, we are using Leandro's library. So Leandro has some functions that just make some of the things we may need to make a delay much easier to program and not like programming from scratch. So we import Leandro's library, and in the init block, using the _.init function, which is a library, you need to have Leandro's library for this to work. We initialize it. Then we are leaving a bunch of memory. We're allocating a bunch of memory for our delay lines because we are going to have multiple, in our example, we have 38 delay lines that we need to program, and it could even be more. So we need a bunch of memory.
No, actually the delay lines is the number of channels.
Okay.
We are doing the effect so that it's not only stereo, it's multi-channel, but the number of taps is just how many times you're tapping into the single delay line of a channel.
I see. So yes, so with the underscore memory new, we are making sure we are leaving enough memory for our multi-channel effect before we... Sorry, someone's calling me. I'm just going to assume this is a telemarketing scam and not pick up. Then, so here we are beginning the... I'm thinking of how to call this, like the channel enumeration process. So we're starting at -1.
Yeah.
And since channel 1 is channel 0, at the beginning, this is -1. When the loop begins, it's going to be incremented. So 0, 1, 2, 3, all the way up to 63. And that's the maximum number of channels per track in ReaFIR. Sorry, Leandro, were you going to say something?
No, I think that you're explaining this right. Yeah. At most, we'll have 64 channels, but typically we'll have two.
Yeah, like I can't think of a 64 channel situation. The most I've had in my life has been 26, which was a 24.2 room in a university. That was kind of, and that's like a very experimental kind of fun thing. So the loop begins, and the loop goes, like the loop repeats number of channel times, basically. Right, so if it's 2 channels, then the loop is going to run twice, and it's going to, so then here we are allocating a place in our memory for a circular buffer. And because we didn't want to constantly write values of this circular buffer in like samples, we are using this other function that Leandro created, which converts milliseconds to samples. So we say 20,000 milliseconds, which is 20 seconds, and it does the calculations to samples. And Leandro, if I change my sample rate, this function will know. This function is taking the sample rate and doing that math. So right now it's 960,000 because I'm at 48K. If I go to 44.1, it'll do the math for that, which I don't want to do right now. Yeah,
Correct.
882,000 in that case. Cool. And a circular buffer, so a delay, whenever you create a delay, you are storing sounds you're storing incoming signal into a buffer. You're releasing that sound at a time in the future, which the user controls with the rate. We are doing it a little bit differently, but basically we need a circular buffer to constantly store incoming signal and then let us release it at the time that we wish to release it. And then I'll get to the comments in one moment. So the serialize block, we just created one line in it just for it to exist. But I don't remember why we had to do this. Can you remind me?
Yeah, so the thing is, on the init block, we want to initialize the delay lines 1 per channel. So we need to know the number of channels in the init block. This num ch variable that we want to use in the init block usually is not defined in the init block. But if we define a serialized block, we don't have to do any work there. We just have to have one. We just need a serialized block. But if you have a serialized block, then ReaFIR will not zero out all your variables before running the init block, which means that we have access to the number of channels in the init block so we can initialize the delay lines correctly. So it's kind of a hack, but it's also okay because we probably are going to need a serialized block at the end of the day, so it's fine.
Cool. And I guess moving on, I'm going to skip over the slider block for a second to get to our, or I guess I'll just skip over this line for a second so that we get to our kind of main event formula, which is written here. And watch the last episode to see how we arrived at this formula, but we took a physical formula from Equations of Motion Wikipedia page, which you can find the link to below. And we simplified it to get to this situation. So this 1,000 just turns a second value, a value in seconds, to a value in milliseconds. But we're taking the square root of the initial position, that's where we dropped the ball. We're timesing it by 2. We're dividing it by the acceleration, which the user sees in g amounts, meaning 1g is Earth and 0.3g is Moon and 2.3g is Jupiter. But then we translate that number into an acceleration to plug into this formula. And then in the sample block, we're running a loop, and in our loop, we are we are basically creating a delay line and then storing the variable delay lines per channel in there. And circular, so I asked you this last time as well, but I need to ask you again. What was the difference between buffer push and buffer get?
Okay, so what we are doing there is not creating a delay line. The delay line has been created in the init block. We are just getting it. We are just fetching the delay line that exists already in memory. We have already claimed that space in memory. All we got to do is just use it. So when I say use it, I mean either you want to push some samples into the delay line, a sample came in and you want to remember it for later, so you push it into the delay line or into the circular buffer. And that's what we are doing on the push line. We are getting a sample for that channel, pushing it into the delay line, so it will be available to us later. And then on the next line, we are using get to, well, retrieve, to get a sample that has been stored in the delay line in the past. How much in the past? Well, that's the time of the bounce. So if the bounce is going to happen 0.45 seconds after you drop the ball, we are going 0.45 seconds into the past, fetching that sample from the delay line using the get method. And then where you see SPL channel plus equals, what we're doing is we are mixing the dry signal, which is just SPL at channel. That's the sample that came in. We are mixing into that dry signal the sample from 0.45 seconds ago. So that's the first bounce.
I see. So here we create the buffer, but in the init block, we don't have access to the sound. In the sample block, we get access to the sound. We push it into the buffer, and then we retrieve it based on the time. Okay, gotcha. So John says, hello, John. Thanks for being here. A slider for channel offset might be nice, like some amount of panning for each bounce. Okay, I'll add that to the list of stuff we got to do. Also, when I recreated this with when I recreated this effect with ReaDelay, or made like an approximation of it, I had a situation where at the beginning the bounces were mono, and then their width increases as you go to the next taps. So at one point we'll be recreating that as well. And Bo says, the channel loop thing, does it automatically detect the number of channels used for the plugin? Yes, right? Because this is, if I go to this plugin right here, right now we have 2 in, 2 out. If I make this 4 in, 4 out, or 64 in, 64 out, or 64 in, 2 out, or whatever it is, the JSFX will have access to that information using. So basically, this I don't know, should I call this variable? This variable fetches the number of channels from here. So did I leave anything out? Oh, and when we are getting the buffer, we are using the negative of bounce time because our bounce time is a negative value. Is that correct?
Well, bounce time is a positive value, but we need to get samples from the past. So the offset is negative. It's like when we were working on the EQ, we had xn-1, xn-2.
Yeah.
Well, we don't have the n, but we do have the minus something to go into the past.
I see. Okay, cool. Makes sense. So yeah, I think that's what we've done so far. I think that's about wraps up what we've done so far.
Yeah, and as far as I remember, this works. If you put some audio through this, you are going to hear the first bounce. It's only going to be a one-tap echo, but it is going to be on the right time.
Yeah.
And if you drop the ball from further up, a greater height, it will take longer to do the first bounce, to do the first step of the echo.
Yeah,
am I right?
Let's try that. I just sent this sound to where our ball drop is, and if I play, we have the first bounce.
Yeah.
like that.
All right. So I think that the next step on this puzzle, you can actually see stuff that I pasted on this code share that Arya has on the right, is on the Wikipedia article for the equations of motion, there are actually 5 flavors of the equations of motion, and we're going to use 2 of them. The second one that you see on the screen is what we used last time. It is how to calculate the final position, and we massage that formula to actually compute the time. So we resolved this formula for time because we know what the final position is. It's at the desk. And we know what the initial position is because it was given by the user with the height slider. So let's say 1 meter from the desk. We already have the position final. We have the position initial. And we have the velocity initial because you're just letting the ball go. You're not throwing the ball. So the initial velocity is 0. And then we just resolved that formula for time. And then and that's the formula that you see that is mentioned as bounce time .1 in the code base. Now we need to compute the velocity at which the ball is going to hit the table for 2 reasons. First, the velocity that the ball is going to hit the table determines the velocity that the ball is going to leave the table going up for the next bounce. We are going to need this velocity to be able to compute data about the next bounce. And the second reason is the velocity that the ball is going to hit the table at determines how much of the sound we are going to hear. If the ball hits the table faster, it is going to make a louder noise. And if the ball hits the table more slowly, the sound is going to be quieter. The bounciness of the ball, if it's going to go high up or not as much, as well as the loudness of the bounce, they're both determined by the final velocity. And that's why I have pasted the first flavor of the equations of motion on line 3 of the code share. And I just rewrote what you would find in the Wikipedia article using variable names that are more explicit. But with this formula, we can compute the velocity at which the ball is going to hit the table. And then we are going to use this velocity for the 2 purposes I mentioned. So all of this is determined by the sliders. We don't need to do this at the sample block. We don't need to know what the sound is going to be for us to be able to process the velocity and the positions and the times. So we can calculate this on the slider block right next to where we are computing the bounce time. We can compute the bounce velocity or the velocity of the ball at the time it is going to bounce.
I'm going to comment that with this, we are calculating the... Whoops, wait. Am I doing the comment thing wrong? Is it not 2 dashes? Oh, no, because this is not...
That's in Lua. In JSFX, you use slash, yes.
So this is the position of drop. This is not a good way of wording this.
Well, actually, it's more like the time. Because the position we kind of know. The position is where you left the ball, and the position final is the desk. So, and we are calling the desk 0 in our scenario here. We are saying that the desk is at position 0, and then the positive axis is going up. So you're letting go the ball at position like 1, which is 1 meter, and it's going to go until 0. And at that point, it's going to hit the desk. So we already have bounce time. And in the formula, we need acceleration. We have acceleration. Time, we have it. We are calling it bounce time .1. So you probably want to rename that time variable to be bounce time .1. And the velocity initial, we already know it's 0. So you can just rename the time variable into bounce time 1.
I was also going to say something
remove the velocity initial.
About the bounce time 1. To me, it makes sense if it was bounce time 2, because our dry sound technically is the first time we drop the thing. You know what I mean? Like, so if we're pretending like the delay is a bouncy ball, but our ball itself is the sound. So the first transient of the dry signal is actually kind of our first drop of the ball. And then our delay creates the subsequent drops. Do you know what I mean?
I understand that, but that's not how I conceptualize this. Let's see if my way of thinking about this makes sense
Okay.
to you all. I think of the sound coming through without any delay being the dry signal, and I think that maybe we want to have some kind of dry wet slider. But I think of that as the dry signal, and then I think of the bounces as the wet signal. So if you even had a dry wet slider, you could just completely mute the initial sound and just have the bounces, if that's useful for you for whatever reason.
Okay, yeah, I dig that. Cool. So bounce time 1, and then was there something else I need to change? Well, no. Okay, we talked about that. I guess, are we okay with these
Yep.
variable names otherwise? Velocity initial, acceleration, we already have. So that's good.
You can remove the plus velocity initial because velocity initial is 0, right?
Right, we're never
So you
gonna,
can
yeah, we're
just
never gonna have
remove that.
throwing the ball. We're just dropping the ball. And
yeah. Now, next, so now we have the velocity. We just need to use it. And I said that we would use it for 2 reasons: to calculate the loudness of the tap and to compute information about the next bounce. So let's start with the sound, how loud or quiet this is going to be. So the loudness of this step. It is going to be a factor of the velocity. And it is also going to be a factor of something that I don't think we have a slider for that now, but we need to have, which is the bounciness of the ball. Is this a ball that bounces a lot when you leave it, when you let it go and it bounces? Does it come back almost to the same height, or is it more of a heavier ball like a marble that is going to hit the desk and it's going to bounce, but very little? And yeah, I was calling this elasticity. I don't know. I'm not a physicist. So if you all know a better name for this variable, then be my guest. But right now, I think I'm calling it the elasticity. So that is a number between 0 and 1. And that is the coefficient of how much energy the ball is going to lose in terms of sound and how much energy is going to be used to get the ball again back up.
And it can't be 0, 0, right? Like the first value should be something like this, right?
Well, if it is 0, then the ball is going to fall and it's not going to come back up.
Okay.
So if it's 0, it just means
like a bowling ball.
it's a one-tap delay. And I don't know if that's useful at all.
But yeah, it's not physically impossible. So let's keep it. So let's call this, I guess we will also call this just elasticity for the user. Why not?
Yeah, I'm pretty sure that someone is gonna correct me. I'm
We'll
not
correct it if
that well versed
somebody
into this.
presents us a good argument or presents a better name. We're always happy to change this stuff. So now we are.
All right. So
and here's my question: do you think? I guess because, okay, when it came to planets, we were like, maybe it's better to use planets as presets and then for gravity, just give them full control. Do you feel the same way about elasticity, or should it be like a drop-down menu and they can choose like bowling ball, ping pong ball, golf ball?
Yeah, I think that would be nice. We could, I think we can start with the slider, the same thing we did with gravity. We can start with the slider, but then we can find some values that work well, and then we can have sort of a preset situation, but not really presets, though we could have presets for the effect. But I was thinking just maybe we could have a drop-down menu with a couple balls and then some custom option. And if you enable custom, then you get to see a slider and then you can move it around.
Sounds good. Sounds good to me.
Yeah. Okay, so now we need to compute I'm going to call this the loudness or maybe the gain. I'll let you decide the name, but it's this notion of how much of the energy of the velocity is going to be converted into
what about
sound.
Amplitude?
Fair.
Cool. Amplitude. So I guess how should I say it? Because we are relating this amplitude to the bounce time 1, and then each bounce has its own amplitude, right? So, what's the kind of coder's way to relate one variable to a corresponding variable?
Well, right now, let's not worry too much about this because I think that most of these names are going to change when we start the loop to calculate the next bounces. So, yeah, amplitude.1 is okay. And I was thinking that maybe it could be a factor of the velocity. Now, let's think about the units of measurement here. The velocity is being given in meters per second, and the amplitude needs to be given, well, in a number between 0 and 1. We could have negative amplitudes, and then we would be inversing the phase of the output, but let's not get there yet. Inversing the phase of the latapes is actually something useful, especially if they come too close together. Then if you have all of them just being positive, then you may end up with some destructive interference. But for now, let's just leave the amplitude between 0 and 1. But I don't know exactly how to convert from one to the other. I think we need to come up with a magic factor that is going to be, maybe there is an equation for this, but I don't know about it. So that is going to relate the velocity to the amplitude.
Could we just do this in a scale base? So just as an example, if the velocity is 100 meters a second, then it's full volume. And if it's 1 meter a second, then it's near nothing. And we just relate these two scales to each other rather than like compute it kind of exactly.
Yeah, I was thinking about something like that as well. And I think that in reality, if we were trying to model this accurately, there's probably some formula to relate these two, because if you have a notion of the mass of the ball, then combine the mass with the velocity and you have the momentum. I don't know how they call this. And I think that would give you some notion of what is the amplitude of the sound being dissipated. But let's just do your idea because I think it's fine. So we'll have to calibrate this to actually have something that makes sense. Like, we know that when we are dropping the ball from 1 meter, it is going to reach the desk with
9.8.
No, that is not the case, I don't think. If the ball falls for a second, it's going to hit the desk with 9.8 meters per second of velocity. But 1 meter does not correspond to 1 second necessarily. In any case, intuitively, it seems to me like the range of 20 meters per second could be full range. And then anything lower than that is. But the other thing is, all of this this conversion, I don't think it should be linear. I think it should be logarithmic, because the amplitude of like a half is going to be a lot more noticeable than going from a half to 0.25. Right. So I thought that maybe we could do this with a logarithm. What do you think?
Sure.
Okay, so let's say that 20 meters is full scale, and we are going to use logarithms for this. So I was thinking that maybe we could do this using the, I don't know, I'm making things up here, but I was thinking that maybe we could use the formula to convert from amplitude to dB and then back. Yeah, and I have implemented that formula as part of my library. So here's a cool trick. Double-click the import leafac.jsfx inc, and you're going to see the source code for my library. Isn't that cool? I didn't know this feature. Yeah, and you can see there the amplitude to dB function and the dB to amplitude function. Now, we could just call this, but actually we don't want to do that because those formulas are expecting amplitudes and dBs to be in this range of -1 to 1. And in our case, that's not what we have. We have a range that goes from a velocity of 0 if you're dropping the ball when the ball is already at the tail, so it's not going to get any velocity, up to, we are saying, 20 meters. So these formulas, as they're written, they expect the amplitude to be at most 1.
Right.
And in our case, we have an amplitude, which is actually a velocity, that is at most 20. So there is a variation on this formula that allows you to have a different range.
In your library or in the world?
But the thing is, in the world, actually, I made a video about this, but now that I'm saying this out loud, the formula, if I remember correctly, boils down to dividing. So when you see in the formula 20 times log 10 of the absolute value of amplitude, you just divide by 20, or sorry, you divide by the range, which in our case is 20. You divide the amplitude by 20. So we might as well just divide by 20 and then call the library function. But the issue is we would get a value in dB. So in the end of the day, I don't think that maybe this log thing is going to pan out. So let's just divide the velocity by 20 and call that the gain. Sure. How about that?
I had also another suggestion, which would be, instead of calculating the amplitude, we create a way of just taking volume away from the incoming signal, if that makes sense. So we just say, oh, bounce 1 is at whatever incoming loudness it is, and then bounce 2 is like 90% of that, and bounce 3 is 85% of the original. Do you know what I mean? So instead of calculating it in dB values, we just look at the incoming signal and we just divide it by an amount that we have control over.
What you're proposing is kind of like a compression of the gain on the delayed signal, which is an interesting concept. You're like putting a compressor on the delay line, more or less, if I understand correctly, which is an interesting concept. But I think we should start with the simpler thing, which is just take velocity final divided by 20, and we are calling that our amplitude. And that's the story.
Velocity final divided by 20. And then we plug this into another formula, right?
Yeah, so on the lines, on the sample block that read SPL of channel plus equals blah, 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 what we want to do is to multiply. So on that line, we are getting something out of the delay line. We are getting an old sample and we are replaying it. So all we got to do is just replay it at a lower volume, a lower level. So you just multiply amplitude 1 and you're good.
So I'll just go amplitude. Sometimes it decides not to suggest anything. I love that. And that's because I misspelled it, but it was honestly not doing it from the beginning. That's it, right?
Yeah. That is it. There is a small issue, but we'll get to that in a moment. For now, let's try this. And I see you muted, Master. Just make sure that whatever routing situation you have, we are not listening to this right now, because if we got this number wrong and the velocity is not in this right range and the amplitude is going to be huge, then we'll hear a huge sound as the first step.
So I'm mastering my mute. I wonder if that automatically also mutes this. And I guess I'll do this test when the risk is less. Oh, yeah, well, whatever we did, it triggered this situation.
It auto-muted. Yeah, so let's look at the effect, the development environment in ReaFIR, and look at the right pane and see what the variables look like. So amplitude 1, for instance, is that number between 0 and 1 as we expect, or is that number
625?
That is a big number, sir. So let's look at the velocity final to see if that makes sense. Velocity final is a huge number. So that doesn't seem right to me, does it?
Not. So our bounce time, that is, even our bounce time is pretty large. It should be like half a second. It's 21,000. Oh, milliseconds.
Oh, I see the issue. I see
Okay,
the
go
issue.
on.
Yeah, the issue is the unit of measurement, because we were using the bounce time to get the old samples. So we actually computed the bounce time in terms of samples. That's why we have a call to milliseconds to samples on that line. But then on the next line, we are using the bounce time as if it was in seconds. So we need, oh, yeah, I guess we can do the thing you're doing, but that's kind of silly, isn't it? We should instead have a variable that is the bounce time in seconds, and then have another one which is the bounce time in samples, and then we use those variables in the right locations.
Okay. So goodbye this thing. Oh, cause yeah, I see. We're like, I see what's going on. Yeah, we're like changing it to samples from milliseconds, and then we're changing that value, reverting it. It's like inefficient coding.
Back.
Okay. So in that case, I should have a bounce time. What should we call this? Bounce time.
I would call it bounce time dot one dot seconds.
Okay. Cool. And this will be just this formula.
On that variable, you can just, yeah, you don't get the 1000 because the 1000 is converting the seconds to milliseconds. You just get the square root and up to the end of that equation.
And I think I'll have to.
And you cut that, you remove it from there and paste it on the other line. That's right. And then we will define another variable, which is bounce one samples. And that one is just milliseconds to samples, 1000 times bounce time 1 seconds.
Ooh, I wish these texts would wrap. And I think I'll need to get rid of one of the brackets too to make this. Or I wish just shift and scroll wheel would work, but come on now. Here.
Yeah, this is super uncomfortable, and that's why I use Visual Studio Code for most of my JSFX.
And this is also an argument against explicit nameage of the functionage.
Yeah, that is an argument. It's just not a very good one, I don't think.
Okay, so here we are using bounce time 1.seconds, and now Bob is our uncle.
Yeah.
And I'm going to save this.
Yeah, but we do have to go and revisit the line and the sample block, which is using the bounce time 1, and you need to change that guy to be in samples.
Samples, and I think so far.
And now I think we have it. So let's restart this and check it out. Now the amplitude, we can already tell that the amplitude is between 0 and 1. So that's good. And it's at 0.22, which is like minus 12 dB. It is somewhat quiet, but it's not terrible. And if we wanted to make this louder, we could just by changing that 20 in the formula to a 10. That is going to make everything louder.
Well, let's see if this is a legal or... Okay, this looks reasonable. Should we listen to it?
Yeah, let's listen to it.
It's much quieter. It's 12 dB quieter.
I don't actually hear even the first bounce.
You don't hear... Oh, because...
Did you mute me?
No, I muted this. Nobody heard that. Okay. There we go.
Yeah, it's much quieter. So mission accomplished in the sense that we are applying the gain corresponding to the energy of the ball. Now, we can have maybe a slider for this, which is like this coefficient that determines the translation between velocity and amplitude. Or we can maybe find a good value and just let it be. Whatever the case may be, I think we can move on to the next interesting part, which is to compute the information about the next bounce.
Sure. One thing I would say about this, not that we need to address this right away, what I find interesting, at least with a ping pong ball, is that the velocity between the first two doesn't change at all. and then it starts to go down, and then it goes up a little bit, which is very interesting too. So I just thought to observe that. Funny.
Yeah, so I think that would be because of imperfections on the ball, or I don't know. I don't know really how to explain that.
But yeah, it needs to be like if it goes down 12 dB by the first bounce, I feel like that's hella extreme. You know what I mean? Because...
So change that 20 to a 10 and let's hear that and see if that makes more sense.
Sure. Joinks, and this is annoying. I would even like, and again, we can kind of visit this, like do this like 3 or something. Yeah, because I feel like if we do like 20, by the time we get to the third tap, we're already like, I don't know, 60 dB quieter. I'm just throwing numbers out, but you know what I mean? Yeah.
Yeah, and that's the interesting and fun part of developing a plugin, I find. Yeah, looking at the equations on Wikipedia and then implementing them and seeing them actually work is all great fun. But really the craftsmanship of developing an effect is this calibration of the parameters and even this consideration of, is this something that we want to present to the user, or is this something that we are just going to find a good value and let it be? And all these decisions add up to a good experience or a bad experience. And I think that's where the R shares, and that's what I find interesting.
In fact, we can make this a variable and I guess make it a slider, right? So cool, we'll decide on that.
Yes.
Awesome.
Yeah. Now let's look at the next bounce. We need to compute, we need to compute about the same information, right? We need to compute the time of the next bounce and the velocity of the next bounce.
Cool.
Right? So
should
the
I,
velocity of the next bounce is actually
this velocity final one, because we need more of this, right?
Yeah, whatever you want to do. We are going to do all of this for 1 bounce, then for 2 bounces, and then we're going to create a loop to do for n bounces. Yeah, but if you change velocity 1, you need to make sure that you're changing it everywhere. For instance, on the line that is calculating the amplitude, you need to change that as well.
And I think looks good.
All right. So let's start. So we need to compute two properties of the next bounce. We need to compute the time when it's going to happen, and we need to compute the velocity so that we can compute how loud it's going to sound, and we'll need that velocity for the next bounce, the third bounce. Okay, so the velocity of the next bounce is actually kind of easy. Think about it this way. The ball is going to hit the table, and it's going to go back up, and it's going to stop.
Yeah.
And then it's going to come back down and hit the table again. So we are not taking in consideration air resistance. We are not taking in consideration imperfections of the ball or drifts of the air or whatever. We are pretending that this is with a perfectly spheric ball in a vacuum. So in that case, there is nothing that is going to take away energy from the ball when it is coming back up and then back down. So the velocity that the ball is going to leave the table at is going to be exactly the same velocity that the ball is going to reach the table again later. There is nothing taking away this energy. So it's going to lose speed as it goes up, and it is going to regain that velocity when it comes back down. I used the word speed incorrectly. So it's going to hit the table with exactly the same velocity that it goes up. Now, we know the velocity that the ball reached the table at, but that velocity on the first bounce, when it reached the table on the first bounce, it's not the same velocity that it's going to leave the table at because the ball lost some energy in the process, namely in the form of sound. We heard that bounce, so it lost some energy. So now we need to use this elasticity factor to determine the next bounce. Sorry, the velocity coming back up. We have the velocity final 1. So to compute the velocity initial 2, that is the velocity final 1 times the elasticity. If the ball is elastic, it's going to bounce higher, which means that it's going to leave the desk with a higher velocity. And if the ball has less elasticity, it is going to just bounce less. And the velocity is going to be lower. And the elasticity needs to be between 0 and 1. So 0 is the velocity final 1 times 0 just means the ball falls on the table and doesn't go back up. And elasticity of 1 means the ball is going to reach exactly the same height it left. So it's going to bounce forever because there is nothing else taking away this energy. And if we had an elasticity of greater than 1, then the ball would gain energy as it hits the desk, as if you were the desk. So we are saying that the desk is not actually stationary; it's a hand that is bouncing it back up, which is something you could do. Like you're like hitting the ping pong ball. But I don't think that's what we are going for. So let's leave the elasticity between 0 and 1, and maybe we even want to calibrate this further so that you don't go that far.
What's interesting to me is like elasticity of 1 is almost like a feedback at 0 dB or a feedback of, you know what I mean? So that's cool. All these things are beginning to relate to real delays. Real nerdy stuff. Love it. Love it.
Yeah, it is. It's lovely. Yeah, I'm having a lot of fun. So, all right. So let's compute the variable called velocity initial 2. And that's easy because it's just velocity final 1 times the elasticity.
Whoopsie daisy. Times elasticity. Shabloinks. I'll do this.
Yeah. So with the default values, it means that the ball is going to hit the table with a certain velocity and it's going to leave the table with half of that velocity. Now, there is an interesting phenomena that is when the ball hits the table, it does not come back up immediately. It takes a fraction of time to actually deform and then come back up. But I think that that time is negligible, so I'm not going to worry about it. I'm just going to think of the time. So we have a notion of time going on as well. The bounce time 1. So this time of the ball arriving at the desk and the ball coming back up is negligible. We are just going to pretend that they're the same. So now we have to compute the time of the next bounce. Okay, so let's think about it this way. The bounce is going to happen as the ball moving from velocity initial 2 up to velocity 0 when it stops in the air, and then it's going to come back down and reach velocity final 2, which we know to be equal to velocity initial 2, because we are not modeling any sort of loss of energy in the process. Great. So we can think of this trajectory as 2 parts, going from velocity initial 2 to 0, and then coming back down. But because we are not modeling anything else, we can think of these 2 parts of the trajectory as symmetric. Okay, so what we are going to do is we are going to compute using the second flavor of the equations that we have on the code share thing on the right. We are going to use that formula to compute the time it takes for the ball to go from the desk up to the position where it wants to stop. And we are going to double that.
Right.
right? Because the second part of the trajectory, when it comes back down, is exactly the same. So the time it takes for it to do the full travel is double the time it takes for the ball to reach its stationary position when the velocity is 0. So now we need to massage this formula so that it works for us. Well, first, let's use the formula that we... the formula on line 3, the first flavor of the formula. Let's use this formula to compute how long that will take. So we know that the velocity final is the code share updating when I'm writing things? Yes. So the velocity final we know to be 0. We are interested in the point where the ball stops. The acceleration, we still know what this acceleration is. It is actually negative in our case because the acceleration is going down, and we are considering that the axis going up is positive. So we need to call the acceleration minus acceleration. And then we don't know the time. That's what we are interested in. But we do know the velocity initial. We are calling it velocity initial 2 in this case. So all we got to do is resolve this for time, and we'll have a formula for computing the time of the third bounce. Am I right? The second bounce. The time of when the second bounce is going to... and of course, we need to remember to double this. So I'll leave a note here. Double this. Cool. But let's resolve this for time. So the first thing I want to do is to take this number that is being added, and I will move it along to the other side, but subtracting. And then this minus acceleration guy that is multiplying, I will pass that guy by dividing, and then these two negatives become a positive, and we have an equation for the time of the second bounce. Well, not quite. We have an equation for the time when the ball is going to stop in the air.
And then we times that by 2.
And that's all fun and games, but I'm going to call this the time of stop. And then the time of, I'm going to call this time 2 for the time of the second bounce. It's just double the time of the stop. And I'm writing these as 2 different variables because we are going to need this variable later.
Interesting.
Well, actually, we need this variable. We actually need this variable for something that we'll tackle much later. We will need this variable, but we are going to need this variable to plug it into. I will explain what I'm thinking about. So we'll need this variable to plug it into this other equation to compute where the ball is going to stop. We already know when the ball is going to stop, and we know how long it is going to stop.
How long it's going to take for it to get to the stopping point?
Yeah, we know how long it's going to take, but we don't know where that point is. To calculate where that point is, we would need to do this. But we don't need that right now, because we already computed the velocity using that other trick I mentioned of just using the notion of elasticity and whatnot, and the fact that we are not losing energy along the way. But why would you need this position? Well, if you want to the graphical user interface that we want to have for this, we want to draw the trajectory of the ball. For that, you need to compute the position. So to do the sound portion of this effect, we don't need this time stop. But for the graphical user interface, we will need this. And in fact, I would argue that the graphical user interface for this effect is much more interesting and much more complex than the sound of it. Because for the sound, we can get away with not calculating everything about this, but for the visuals, we'll need to compute all the positions, like when is the ball going to stop, but where is it going to stop? How high is it going to go? And we'll need to do, I was imagining this interface that I think is super cool, and it's super interesting to compute, which is like, imagine the drawing that you actually had on the thumbnail for this stream, that is like the ball position over time. So imagine that graph, and imagine the sound wave. So the drawing of the waveform going through that trajectory, and then you would see the sound wave. When the sound wave reaches the desk, you hear a sound,
Cool.
and then it bounces up, and then it comes back down, and it's going to follow the curve of that graph.
That's beautiful.
That is the trajectory or the position over time. And then you would see the sound wave and you would hear when it bounces. And it could, of course, get smaller based on the amplitude one that we have. So you would see the effect. And I think that is a super neat graphical user interface.
Yeah, I am very excited about getting there in a bit, you know.
Yeah, it will take a lot of geometry and a bunch of math, and it will be a lot of fun. But let's just get the sound right first. Okay, so I kind of already wrote everything that you need to write, but I think it's a good practice for you to rewrite this instead of just copying and pasting. Or if you want to copy and paste, you know what?
Sure.
It doesn't really matter.
I'm gonna call this not like I'm giant fan of time stop, or so I'm trying to think of it's bounce. It is a bounce, but it's bounce hang time stuff. That's not great either. I'm gonna go with this. So we got bounce and we got hang, right? So bounce is the moment of collision, hang is the moment above. And I'm just going to call it hang time. What about that? Hang time. And even though it's the first hang time, I think I should call it hang time 2 for easier mind not being fucked stuff. Whoops. Come on, tab thing. You're really selling me on Visual Studio Code today, ReaFIR IDE. And divide that by acceleration and shablamps. So I'm also taking note of these. So this is time for ball to get back to the drop zone. It's not a good name. To initial height, I'm just gonna call it. It's hard to name stuff.
It's not going to reach the initial height. That's what's interesting about this phenomena. It lost some energy in the form of sound when it hit the desk, so it's not going to get back to the initial height. It's going to get to some height based on the elasticity.
Position. I'll edit these terminologies. Actually, my mom would be a great person to ask this because she translates textbooks. In the realm of like engineering and stuff, so she would probably know. She'd probably be a good person to talk to this about.
Oh, I know what to call this. This is the peak. You can think of this as like a curve of a parabola of position over time, and then that's the peak of that parabola.
Sure. So this is peak time to get to I'm just gonna call it time for ball to pick before dropping again. And this is self-explanatory, but I'll call it anyway. Velocity of the first bounce back up. And now bounce time 2.seconds is gonna be it's just gonna be 2 times peak time. Well, I said and I realized that. Shabloinks, boop. That looks like something. And now we need this in seconds, and we need to also calculate this in samples, right?
Yes, that's what I was gonna say. We need to calculate the bounce time in samples,
which is gonna be like
so that we can actually mix this into our signal.
Oops, copy joinks, and I'm just gonna simplify this. Do you object to simplifying it that way? I actually do. Yeah, I'm gonna.
I object to that. I think you should be using the bounce time 2 seconds in that position, so you don't need to multiply by 2, and you don't need to use peak time 2.
Wait, no.
Do you see what I mean?
Say again.
Instead of saying 1,000 times the formula to compute the bounce time to seconds, right? Because that's what you have
Oh,
there.
okay,
You have
okay. I see. I
1,000
got you.
times 2 times peak time 2. Instead of just use the variable, we have
Gotcha.
computed that
Yeah,
in the
yeah,
previous line.
yeah. And I feel like syntax is fucky here. Yeps. And like that. Recompiled. Okay. Woo. Woo. All right. I like this tab situation
And let's
that
look at
they
the pane on
have
the right.
up here. I like this
Sorry?
tab situation we got up here where we can tap to your library and back.
Yeah.
Lovely.
Yeah, it's very nice actually. I mean, it keeps surprising me like how good it is because I expect so little from it. But can you expand the pane on the right so we can see, and that's one of my favorite features on this thing, so that we can see if the bounce time 2 in seconds makes sense?
Yeah, makes sense. 0.9, which is almost 48,000 samples. That makes great sense to me.
All right. So in that case, let's compute the amplitude of that second bounce.
Okay, let me see if I can
Which
do
again
this.
is going to be.
Let me see if I can reason about this without your help. Actually, to do that, we need to first get the velocity, I guess. Velocity final 2. Is that correct?
That is correct, but we have computed the velocity initial 2, and we have determined that because it's not losing any energy along the way, the velocity final is equal to the velocity initial. So we may just want to call it velocity 2. I don't know.
Okay,
it's up
yeah,
to you.
I can deal with that. And then so I won't need to recalculate. I just go amplitude 2 equals velocity 2. Whoopsie daisy. Amplitude 2 equals velocity 2 times acceleration. No, velocity. It's going to be velocity 2 plus this value that arbitrarily. Oh my god. Can you type, Arya? Thank you. That we arbitrarily just called 3, and I guess we're keeping it 3.
Yeah. At that point, this 3 is giving me a bad taste, so I think we should have a variable for this. I mean, it will be just magic variable equals 3, but at least we'll have a single place to change the magic variable.
I'm going to call this. And you know what would be interesting if it's like at the beginning it's magic variable for amplitude 1, for amplitude 2 it's 99% of magic variable or something like that. You know what I mean?
So you are saying that when the velocity is lower, because that's what's going to happen, when the velocity gets lower, the ball is going to dissipate less energy in terms of sound, or is going to dissipate more energy in terms of sound. I guess that's not really physically accurate. When something is bouncing more slowly, it's not going to sound louder, but whatever. If it sounds good, I'm in for it.
Reverse that,
I'm okay with that.
110% or something, then it's more. You know, then when it's. Well, okay, for now, I'm just going to put a value here. And this one I can set in the slider block. And we may add a slider to it. So what do we call this? This is the... I'm just going to call it sound decay. It's not great, I know. But for now, let's call it that. And we're going to, for now, call it 3. And I'm going to just go sound decay. Take me home. Boom. Zip, 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 boop, zoop, zoinks. Pap, boop. What? Fucked up the syntax there.
I would just say it because it's so easy. It's a semicolon in the line of sound decay equals 3.
There we go.
Yeah. It's just a silly thing.
All right. So let's see. So now we gotta now do this for our second line as for our second bouncage.
Yes.
And I know you don't like to copy paste, so I'm assuming you are now cooking up a loop.
Oh yeah, we will have a loop that will compute all the bounces in one pass, but for now we are copying and pasting. I mean, look at the lines
They're very
above. They have a
similar.
lot of
Yeah.
copy and pasting there. So we'll have some copy and paste in the sample thing as well. So the whole thing from amplitude.1 to the end, just copy and paste it because we are going to do it again.
And I'm going to call this
So
2.
yeah.
And we're going to call this bounce time 2 in samples. And delay line will remain the same. And I'm assuming here we got to add another times, or what do we add there?
No, you just, on the previous line, go one line above where you are and replace the semicolon with a plus, and we are off to the races.
Cool. Beautiful. And
see, now we are adding 2 taps into the delay.
Yeah. Beautiful. And
all right, let's hear
time.
this.
I know that this is not going to do the thing, but I'll do it just to train my muscle memory. Whoops. And I should train my muscle memory not to press space before focusing the arrange again. Okay, that looks good. And our amplitude somehow went up, which is interesting. I'm gonna bring this down a little bit. Let's listen to it too. Cool. Tap, tap, tap. That looks like something.
It does sound like a ping pong ball so far.
Very ping pong-ish.
It sounds like we dropped the ping pong ball on the desk. It hits the desk twice, and then we grab it in the air. That's what's happening so far.
I'm doing something weird right now. Sorry. I'm trying to see just by eyeball if we are decaying a lot or not. We're decaying very slightly. But cool.
Yeah. And one thing to note that is clearly visible on the picture you had on the thumbnail. Can you bring it up? Is it easy for you?
Pretty easy.
Okay. And while you're doing that, I want to say something else that also kind of requires your attention. But Andreas is here. So, hey, Andreas, great to have you here. And Andreas says, hey, you lovely guys. I think that Andreas is talking about us. We are the lovely guys. I have no idea what you are programming and talking about. All I reckon is that Aria's mic is a little low compared to Leandro's. So if you have questions that you want to ask in terms of the code, then please do. And just in general, what we are doing is we are programming this effect that is a delay, but the time of the delay is not determined by like your DAW, like a quarter note, and it's not determined by seconds. It is determined by a ping pong ball falling on the desk, and each time the ping pong ball falls on the desk and hits the desk, that's a delay point. It's a delay tap. So yeah, this figure that you have there, you can clearly see that the bounces are not happening linearly. They're happening exponentially, right? You can see an exponential curve in there. It's not a linear, it's not a line. And the reason for that is something that we modeled accurately. The reason for that is that each bounce loses an amount of energy. And we are modeling that by the elasticity variable that we are multiplying. So each time the ball falls on the desk and we multiply its terminal velocity. No, terminal velocity is not the right term. The final velocity, yeah. So we multiply the final velocity by the elasticity factor. And each time the ball falls, we multiply again, and we multiply again, and we multiply again. And this series of multiplications, if combined, are an exponential. And that's the curve that we are going to see in terms of the height. And it's the curve that we are going to see in terms of the loudness, because the velocity is also determining the loudness. So far, so good. I think this is sounding okay. It sounds like it should. The first bounces are very close to the original gain, but they are going to drop exponentially.
Sorry, in the meantime, I was trying to fix my sound situation by just putting my voiceover chain in here. So that may have just made me sound louder, possibly, I hope.
Yes,
Cool.
you are louder now.
So yeah, sorry about that, Andy. It's because my computer basically just can't handle things the way it used to handle things, and then I just think about it, I get angry because like, why would it not do the things like it used to do the things? But anywhoozles, I hope it's better now. And yes. So yes, you asked for the thing, and here's the thing.
Yeah, so I already said everything I wanted to say about that picture. So we already know how to compute the initial bounce, which is difficult because the initial bounce we don't know the velocity for, but we know how to compute it. So that initial bounce was difficult. The subsequent bounce, the second bounce, was relatively easier because we already had a velocity. So all we had to do is compute the time, and we are computing the next velocity based on the elasticity. So that's relatively easy. Then all we have to do is write a loop to compute all the subsequent bounces. So we already have the initial one. We're just going to create a stepping stone to compute all the rest of them. At this point, because we have something that's kind of working and we are going to mess with what is working, maybe do you want to like create a copy of the effect somewhere so we don't lose it?
What have I become?
Okay.
A copy of a copy of a. Am I right, ladies and gentlemen? I'm going to copy this. We should really be like pros and make a Visual Studio Code situation. But I know that itself is a resource hog, which is why I'm not doing that. If anybody is wondering why.
Fair.
Why? So I'm gonna call this ball drop delay backup. I was gonna call it BU because I call my backups BU, but then I realized Leandro doesn't like that one bit. No siree, Bob. Shabloinks, shablooms. And oh, this is on my voice now. Cool. We got a backup. And here we go. All right.
So it's time to write some loops. And in most cases, when you are writing loops, you also are going to use some memory, right? Because the whole point is that we are not going to copy and paste code. So we are not going to have a velocity 2 variable, a velocity 3 variable, a velocity 4 variable, and so forth. We're going to have a loop. And to allocate all this space for the velocities variables, we need some memory. And so we are back into the init block to allocate this memory. And we need to think about what are the variables that we need to store. I can think of two. What do you think, Arya? What are the variables that you think we are going to need to store?
For our loop, we would need, really all we need is the first bounce time from which we can calculate the velocity and amplitude. I'm assuming we already are calculating this stuff, so I'm not counting those. And then from that, we calculate and with the elasticity, with that, we'll calculate the decay. Really, all we need is to get the bounce time, and we need the velocity final. That's what I think.
Yes. Looking at the sample block, let's look at the variables that we are using there, because every other variable is going to be intermediary. So we are using the amplitude, and we are using the bounce time.
Yeah.
Which makes sense, right? When you have a delay tap, you are interested in when it's going to happen and how loud it's going to sound. That's all we have to store. Everything else is just intermediary stuff that we need to compute in order to be able to compute the amplitude and the bounce time. So how about we have a list or an array? I'm going to use several terms here so that people recognize one of them and they're going to go with one of them, but then I will be consistent and just use one. So the terms that I am interested in here are, you may know this thing as an array, you may know this thing as a list, you may know this thing as a table if you are from Lua, you may know this thing as a vector, many names for the same thing, okay? From now on, I am going to use the term array.
Sounds
How about
good.
that?
Days Rue said, I always wanted to make music, expectations, rocking on stage, reality, channel, equals -1, loop, numcha. Yeah. I always think of it in like film terms too, right? So like, probably Christopher Nolan comes in and he's like, yo, I want these buildings to come fold over these other buildings, and the perspective is gonna get like from the normal way to like an infinite perspective where the rotation of the earth is reversed, and then a bunch of nerds have to sit and code all that stuff, right? So it's like a well-oiled machine. In order for people to rock on stage, then you got people who are like, ooh, how do we make sure as people are rocking on stage that the volume, that the loudness of their microphone stays at a constant range and travels 1,000 meters, kind of deal.
Yeah, for me, what is the most interesting of all is this intersection. How can we make numbers on a screen? I mean, there is nothing more dull than these numbers on the screen. And we are talking about high school physics here. So it's like the most boring experience in our lives. And yet, we can take that and turn it into art. So, I mean, this intersection is just amazing. It's a great place to be. And just making music, I don't think would be fulfilling for my kind of personality. And just working with code would not be fulfilling. But doing both at the same time, I mean, when you have to like tweak parameters, or when you have to think about like the sound decay is going to have an effect on the loudness, and that may be musically relevant, that kind of conversation is great to have.
So let's make that array.
Right. So yes, so in the init block, it needs to be in the init block because we need to do all our memory allocation in the init block. So we are going to have an array, but we need to store in each position in the array, we need to store not one piece of data, we need to store two pieces of data. We need to store the amplitude and the time, right? So before we even define this array, we need to define a data structure, because each position in the array is going to hold a data structure with two pieces of information. In my library, there are ways for you to create data structures and arrays. Great,
yeah,
huh?
let's check it out. Do you want me to kind of go to that part of it? Data structures.
Oh yeah, you can do that. Yeah, right now there is no documentation because my library is very much a work in progress, and you are like a alpha tester of this whole thing. So right now, the data structure that we're looking for is this struct thing. So you can see the underscore struct define method. That's the our function. That's the function we want to call first. So go back to your code, and we are going to call this data structure. How about we call it a tag?
Sure. So I'm gonna go struct dot define. Why didn't it? Oh, okay. Now it happened. Yeah. And let's call this tap, you said. And this is, this goes before, right? Tap.
Yes. And I believe there will be more things that we will need to call taps, like this is the definition of the data structure. When we start using the data structure, we'll also want to call some variables tap. So I propose that we call it tap.struct to mean this is the definition of the data structure, not an instance of the data structure. So this is like the recipe of how to make a cake. It's not a cake. So you have to put the closing parentheses and semicolon
on this line. Oh, okay, we're done with this line. Cool.
Yes. We are done with this line. So now you have a notion of the data structure. We need to put some fields. We need to define some fields into the data structure. So you can use another one of the functions in my library. It is called _struct.define.field, if I remember correctly. But you can go there and check it for yourself.
How come it finds some stuff, but the stuff that it's finding is not correct? Well, I am misspelling one thing, but okay, let's see. This looks like it's something because it went yellow.
No, that's not really meaningful. When the yellow is faded out, you can see the square root below is highlighted in bright yellow. That means it's a ReaFIR function and it knows about it, so it highlights in bright yellow. But if you just put whatever in open parens, ReaFIR is going to think that that's a function call and it's going to highlight in,
I see.
Well, I'm going to say pale.
Well, yellow. This looks right. The name is here. Do you need anything else to read from here?
No, that's all we need. So now we need to call this function, the struct define field, and go back to your code, and we need to pass as an argument the definition of the data structure that we want to add a field to. So we need to pass tap.struct to that. So pass tap.struct as an argument there. And that's all the arguments that this function is going to take. So you can close parens and semicolon. And we need to give this field a name. So go to the beginning of the line and say tap.struct.amplitude or time, whatever you want to compute, to put first in the data structure.
Let's do.
And then we'll have another line that is very similar to this. I think you can copy and paste this line and just change from amplitude to time.
Ship blowing Cerrone. Here we go.
So there you go. That's how you define a data structure. That's just the recipe for the cake.
Yeah.
We have not really allocated any of these data structures now up to this point. That's what we're going to do next. Now, how many of these data structures do we need? In other words, how many taps do you think we are going to need at most? So we are allocating memory here. We need to be pessimistic. At most, how many taps do you think we're going to need? We may not use all of them in actuality. In fact, we are, for instance, in the circular buffer, storing way more samples that we actually need. We are storing 20 seconds worth of samples, but we are only using up to 0.9 seconds so far. So how many taps do you think we are going to need
500. Is that
okay,
too bad?
Do you have that spreadsheet with the bounces of the real ping pong ball? We can maybe take that number and triple
38.
it.
The reason I was thinking of 500, that was 39, or I guess the first one being 0, so it's 38 human bounces. The reason I brought up, or no, sorry, this is just an irrelevant marker. It is 38. The reason I brought up the number 500 was because I see as like a kind of secondary aspect of this is the part where it oscillates, where the time between bounces are so short that it begins to create a pitch. And it won't, that pitch wouldn't exist for a really, really long time. Or if it does, you can, I don't know, put a delay in front of it or copy paste it or whatever. But I wanted to give it like some time to just kind of oscillate as a tone that will be going up in pitch. Like,
okay, so if you think that 500 is the number, then 500 is going to be the number. It's something that we can easily tune later. So now we need 500 of these data structures.
So I go.
You know what this calls for? A loop.
Oh, okay, okay.
No. You can remove that. That's the definition of the data structure. That's not the array with instances of the data structure. So we need an array. We need an array. There is a function in my library to create an array. And So let's give this array a name. We are going to call it taps. So you can say taps space equals space.
Taps, okay.
And then underscore dot array dot new. And then as argument, you need to pass the size of this array, which you said you want it to be 500. All right. So now we have an array of 500 positions. Now we need to put in each position an instance of the data structure. So we need a loop. So go to the next line and write a loop that is similar to the loops we used for
this stuff.
The multi-channel
situation. So I should
situation.
call it something too, or
so in the code share thing, I'm kind of writing the thing that I think needs to be written, which is like something like tap.index. So this is going to be the index into the taps array. We are going to start with -1, and then we are going to loop for 500 times. And the first thing we are going to do is to increment this by 1, so that the first time around it's going to be 0. Now, there is something to be said about this 500, because this 500 is already included in the taps array. That's information that is already there. So the same way we had extracted a variable before, a variable that we called the sound underscore decay, we can do something similar here. We can just get a hold of the size in a way that, so you don't need to extract this variable. Actually, there is a cute trick. We can extract this from the taps array itself. So in the taps array, you can extract the array struct dot size. I think that's how you call that.
Cool.
But I will double check.
Cool. I was just calling a variable, but I'm gonna get rid of that. So I'll go loop, and then the loop we want taps square bracket underscore array dot struct size, which shows up. That's a good sign. And shiblinks, and that looks like correct, right?
Yes, that looks correct to me. And that is a loop that is going to run for 500 times. But if we want to later change this value to 300, super easy, changing it in one place, it will be changed everywhere. Make sure that you have this little closing thing here on your version as well.
I think I do. I don't. Yes, we got to close that loop thing. And that's all this first loop is doing, right? It's just counting up and putting stuff in there.
Yeah, so far that's all it's doing. So let's actually do something interesting in there. We'll go into the taps, and this time we'll not get a hold of the size of the taps. We're going to get a hold of the data in the taps. So this is what you have to write to get a hold of the data in the taps. And then that data, we can just index into that using the tab index. We can go from index 0 to 499. And then in there, what we want to do is to create an instance of the data structure. So you have the tab struct thing. You can use the struct new function, pass that function, the tab struct definition, and it's going to allocate for you an instance of that data structure.
Okay, I'm gonna write the whole code without fully understanding it, and then we can do a little. So struct struct new tab dot struct, and then shiblinks, niblinks. Okay. Let me expand this for a second over your thingamajig, so that we can check out what's going on. Okay. So we defined a struct as this. Then we said we want to put this in a field of the struct that we defined, and we want this in a field of the struct that we defined. Then we are creating an array and giving it a size of 500. And then we are looping through this 500 times. So then we get here. This is not part of that loop because we closed that loop. But
No. It needs to be part of that loop. If you look at my code, you're going to see that I only close the loop later.
Okay, I see. So this situation. So actually, let me do this just for my sanity. I'm going to put this in a new line. Like this, right? And
fair.
And then I do need do I need a semicolon here? I do, I think. Yes. I need a semicolon there. And then we go taps for the number, let's say, of array struct data. So we're pulling data from that loop. We defined them, we looped them, now we're pulling data from them for the tap index, which is from 0 to 500. So this number is from 0 to 500, and then these numbers are unique to the number that corresponds to 0 to 499 for the index, right? So this is a unique number each time kind of deal.
Yes, the tab index is unique each time.
And then that will be a struct new. Yeah, I guess I don't get this function.
So the idea of the struct new is we have a recipe for a cake. That's the tab.struct.
Yeah.
Now go ahead and create a cake for me. So allocate some chunk of memory in which I can store some amplitudes and times. I already told in the previous lines how I want my data structure to look like. Now create one of these so they can actually use it.
Gotcha.
And you have to put
then end the loop, right?
A closing paren semicolon.
So one more of these, and I don't need another semicolon, right?
Strictly speaking, no, but it's better form if you write it with a semicolon there and then a new line.
I agree. Days Drew says, I'm totally far away from coding, but I still want to watch the stream to see how ReaFIR could be customized a bit closer. That's really deep, much deeper than I'd need any time. Yeah, I do all the customized stuff actually, like on my videos. If you want to check those out, I've done a lot of that. And I'll probably do a lot more because those videos are very popular despite the fact that it's all cosmetic stuff. But yeah. But thanks for watching. I hope you are getting something out of this. Sometimes when I don't understand stuff that Leandro does on his streams, I'm just like, it can't hurt to just watch. And like stuff just enters your head and one day it'll hopefully bloom. Because that's how you learn a language, right? You just get exposed to it. So I just watched Leandro's stuff and then one day hopefully it'll stick.
Oh man, I mean, show this code that we have on the screen right now that you wrote, everything in there. So show this code to Aria from last year.
Yeah, exactly.
Yeah. So this has physics. This has it's a novel idea. It's using fancy data structure. It's like you are a coder now.
Yeah, I did something that again was quite simple, but I'm proud of myself. You know, Garant has this JSFX called Piano Display, and it shows you all the notes. And I wanted to show, and then the notes are colored based on velocity. And I was like, it's probably super easy to make them based on MIDI channels, so I can send like an orchestral composition to it, and it creates this like beautiful video. And then I just copied the JSFX, looked through the code, and I found the thing and did some math, and it works. So it's really nice. Yeah.
Great.
Fun stuff.
Fun. All right. Okay, so now we have all the space we need to store this data. Next, we need to compute the data and put it in place. And then later, we'll need to use the data. So to compute the data, we're going to do it in the slider block. And we are going to put the data in the tabs array. Then in the sample block, we are going to use that data to actually tap into the delay line and hear the delay. So let's review what we have and think about what needs to change and what can stay the same. So the acceleration, that stays the same. The sound decay, that stays the same. Then the first bounce is special. The first bounce is special because we don't know the velocity at which the thing is going to hit the table. So we need to do that square root situation to find the first time and the first velocity. Right?
And even the first amplitude, right?
So, well, the first amplitude is based on the first velocity.
Okay, I see.
So, yeah. I'm thinking about where we want to start the loop in this, because some of it's special, like the square root only happens once. So that's special. But I can see the next line, the bounce time in samples, that's not special. That occurs below. See? So that is already a copy. And then the line that reads acceleration times bounce time in seconds, that one is special. That does not occur again. So as a way of reasoning about this, I want to do the following. You see how the velocity final one does not depend on the bounce time one in samples.
Yeah.
Do you see that? So we can swap these two lines and it is not going to cause any issue. Yeah, right. So now we are starting to identify what is the same and what is changing. Put a new line there, right where your cursor is, so we can see that, yeah, these two lines in the beginning are special. And then the line that computes the bounce time in samples repeats. The line that reads amplitude equals velocity final divided by sound decay repeats. And then we have a line that is computing the next velocity. That one is special. It doesn't repeat. And then we have this peak time thing, which is special. It does not repeat. And the bounce time in seconds does not repeat as well. Yeah. All right. So I think we identified the boundaries of the loop. In fact, can you please remove the new line before velocity 2?
Yeah.
Yeah, I think that block that we identified there, that's the body for our loop. That's the stuff that we need to keep doing over and over because that's what repeats. And then we need to define this loop, but this loop I think is kind of special. Usually, all the loops we have written so far, we knew how many times we wanted to run this loop for, right? For instance, we had a loop to allocate memory. We knew we wanted to run it for 500 times. But this time, I'm not so sure that we know how many times we want to run this for. Because we could just have all 500 taps active the whole time, but most of them are going to be so quiet that we won't hear it. So I was thinking that maybe we could take that in account and only activate the taps that make sense up to a certain loudness and up to a certain length. Because if it goes over 20 seconds, I don't want to hear it because we don't have that many samples. We are only storing 20 seconds worth of samples in the delay block, in the delay line.
Yeah.
So I don't know. How do you feel about this? Do you think that we should go into this fancier territory of trying to cap the number of taps, or do you think that it's going to be so quiet, let's not worry about it, let's just have it anyway? How do you feel?
Well, so I guess my question is, say it's too quiet that we can't hear it, but we can always put a second JSFX gain or a limiter or an OTT or something like that. and bring all the quiet parts up to hear them again, right? But I'm also thinking if things that are very, very barely audible without any kind of DSP trickery are going to be using a bunch of resources, then let's not have. So I guess my answer is very ambiguous. It's like, well, let's have it.
Well, that's exactly the trade-off that we have in our hands. If we do this smarter thing of only activating some tabs that we deem necessary, we are going to have less work to do in the sample block, which means better performance. But it means that the code gets more complicated. Usually that's the trade-off. To get better performance, you usually have to write more sophisticated code. So how about you know what, I take it back. How about we start with the simple thing, which is to have the 500 tabs active, no more, no less. And then if it gets too slow, or if we get some sound artifact we don't like because some of these quiet things are adding up or whatever, it shouldn't be the case because it's decaying exponentially. But for a good measure, we can do it later if we deem necessary. So for now, we are going to do a loop that is exactly the same as the one above, where we do the tab index equals -1 and blah, blah, blah. This whole setup is the same. We're going to do something in the body of the loop, but the structure of the loop is the same. So you can maybe rewrite this or copy and paste, however you want to do it. But what you're interested in is the tab.indexLine, blah, blah,
here.
blah. Yes.
So copy that, did you say? And put it in the slider block?
Yes, copy this and paste it. Yeah, paste it there on the slider block where you're saying this is going to get looped. Paste it there. And then remove the line that reads tabs at... Oh, actually, no, don't remove that line. It can become handy. So now this whole block that we have below, from bounce time 1 samples down to bounce time 2 seconds. So we identified this whole block, put it in the loop body.
Wait, what's the smart way of doing this? Command and tab? No.
No, just tab.
Oh, I just select them all and go tab. Yeah, okay. Cool, and then I'll put this thing down here for now.
Yes, and you can remove the lines below that read bounce time 2 samples, blah, blah, blah. It is already in the block, so we know that it needs to be done.
Bye.
All right, so now I think we need to rename some of the variables that are going on there, and we need to rethink the whole strategy. So let's start with the bounce time 1 in seconds above. This bounce time 1 in seconds is, let's call it bounce time in seconds. And let me think about this. Yeah, I think that may be all we need. Right, so you don't need the open bracket. You can just leave it like that. And then velocity final, how about we just call this the velocity? Because what is the velocity final of one iteration is the velocity initial of the next one. So let's just call this velocity.
And then just change this.
And then bounce time 1 in seconds is just bounce time in seconds.
How do you feel about this underline dot situation? Do you think we should just stick to 1, or you're okay with this?
I'm establishing the convention in my own code that you may or may not want to follow. And that is, when you have a word that, or when you have a term that is multiple words, like bounce time is a term, then I separate that with underscore. And then when I have a second word, like seconds is a separate word in this situation, I separate it with a dot. And that's the naming convention you see on my library.
Cool, I like that.
But it's up to you.
Yeah, and then it's kind of like, and I guess we got like bounce time in seconds, bounce time in samples. Yeah, I do like it. Cool.
Great. So getting into the loop, we know the first bounce time and we know the first velocity.
We got to put them in.
So we got to put them in the data structure.
Yes. Question. Right. So we copied this stuff from up here and put them down here. But is it still a necessity to have these in the init block as well? Like create the structure in the init block and then we are re-referencing this loop? If that makes sense. Okay.
Yeah. It is necessary. The loop structure, it looks the same, but it has completely different purposes. The loop bodies are doing something that are very different things. In the init block, it's claiming some memory. It's allocating memory. In the slider block, it is aware of the slider values, and it's computing stuff and storing stuff in the data structure. So one is you have a cake, and now you are going to decorate the cake.
Cool.
And then later in the sample block, we'll be eating the cake, so stick around for that. There will be cake. All right, so let's get the syntax straight here. In this loop line that you have a cursor on, you just need to say up to the first comma, up to the first taps, close bracket, comma, and you can remove all the rest of that line. And then the next line you want to keep, the tab index plus equals 1. That's part of the loop structure, so that one stays. And then go to the next line. On this line, we already have the bounce time in seconds and the velocity. With the bounce time in seconds, we can compute the bounce time in samples, which is what we are going to need. And let's store that in the data structure. So you can say something like the line that we have above. So can you put my code share thing on the screen?
Zoinks. Here you go.
Thanks. I think that to communicate the thing that I want to communicate, it's better to write it down. So what we have right now is this taps index, right? We have this. This is an instance of the data structure, the tap data structure. So we can index into the tap struct time, and then we can assign to that.
Okay.
So maybe we can even separate this in two parts. We can say that a tap is equal to this because we're going to need the tap later on. So we can say that the tap is that, and then you can assign the time to the tap, and then you do some computation there. And later we'll also need to store the amplitude. So we'll have a different computation there. So I think that that's the sort of code that we are writing.
Gotcha. So I gotta basically do in this line that I have now, it says bounce time samples. That's gonna go to the math on line 24 of your code share, right? And then make another one for the well, not exactly for the velocity, but we're using the bounce time to calculate the velocity, and then we'll calculate the amplitude down here, and we store it into the little underline thing of line 25, right? Cool.
Yes.
Do I need to type this again, or that was just to illustrate?
Well, you do need to type this stuff because you need to get a hold of one of the tabs. We have this array full of tabs in there. We need to get a hold of one of these and work with it.
Let me just resize this. Whoopsie daisy. All right, here we go. So I'm gonna go. So the reason we're defining like a single tap as tap, that's just to like simplify our typing later kind of deal?
Yeah, well, there are two advantages. First is that we don't have to write this thing that I highlighted as much, this whole taps and getting the tap from in there. So that has two advantages. The first is it's less typing. Second is it is faster because we are indexing into the memory when we are doing this operation, and indexing into the memory can be slow if it adds up. Now we are on the slider block, so it doesn't really matter all that much because the slider block only runs when you're changing the slider, not every sample, but still it's a win-win
and then
situation.
this that I've done, I gotta change this to samples, right? Before we store them.
Yeah, so you know what? We have a line below that reads bounce time 1 in samples, blah, blah, blah. So how about you just move this line up, and then it is going to read something like this. Bounce time in samples equals blah, blah, blah. And then on the next line, you just say bounce time in samples.
So tab struct time equals bounce time in samples, and I'll go above one line and I will add the line that I copied, right? Whoop-a daisy. And I gotta change this now to bounce time not 1 in seconds, and
and then your comment is lying because it's not computing the time of the first drop. It's just computing the time of the drop.
Oh, sorry. Say again.
There is a comment at the end of this line that is actually lying now because it's not computing the time of the first. It's not the first drop.
So even we can get rid of this line now. Cool. And then, so tab struct time. So yeah, so we'll calculate the thing and we store it in tab struct time, the structure that we defined, or a field in the struct that we defined up there. And put one of these babies there. Cool.
Yes. Then we can compute the amplitude using the formula that you have on the line that reads amplitude.1.
Okay.
Yeah, we can move this line up so it is before the calculation of the amplitude. So I guess I would do this. It's up to you how you want to do this, but I think I would do like all the computations and then all the storage.
I see.
So I would format my code like the thing I have on the screen.
Okay, so we did bounce time sample. Oh, I see. Calculate both, then store both. Not like calculate one, store it, calculate two, store it. I see. A little music for y'all while I type. And I gotta change some of the, so velocity, we just made this velocity. Goodbye, garbage. And amplitude, I guess amplitude 2 we can just now call amplitude, right? And now that I did that, I stored the samples. And now let's store the amplitude, and I'm gonna see if let's see if I can make this work. Whoopsie daisy. I guess first you type it well. Step 1, and I go, this is equals to my amplitude and one of these, and I will then need to go taps at underscore array struct data at tap dot.
No, you can remove that. In fact, the line above that reads taps blah blah blah, you can remove that. We already did this much when we said tab equals taps blah blah blah.
Oh, okay. So goodbye this thing. and bounce time samples, and so we just stored them. And we're...
Yes, we have... Yep,
Cool.
we are good. You are computing the bounce time in samples and you're storing that. You are computing the amplitude and you're storing that. Now, we still have that work below that is going to compute the velocity for the next time we go around, right? We need to update the velocity variable. In fact, there is a very cute way of doing this. And the cute way of doing that is
pseudo objects.
No. It's much simpler. So we have the velocity, and all we want to do to update the velocity for the next time is to multiply by the elasticity.
Oh, wow, that's cool. I like that. Cool.
So that's the line.
And that goes after we already stored the first pack of stuff, right?
Yeah, it needs to happen after, not necessarily the lines that are
at least after
stuff,
define.
it doesn't matter, but it does need to happen after we computed the amplitude and the bounce time in samples. Well, in fact, you know what? Let's think about this for a moment. The bounce time in samples doesn't care about the velocity, and the amplitude does care about the velocity. So we have a question in our hands. Do you want to use this sound decay shenanigans that we're making up with the velocity as it's hitting the table, or as it's going out of the table? It doesn't really matter. All that's going to affect is the calibration of the sound decay variable.
So if we calculate it when it hits, that means that the first instance of delay that we hear is already at a different amplitude. But if we calculate it in the air, the first one will always be equal to the incoming signal in amplitude, right? I like to do it in the air, then I think.
Okay.
So velocity. So then this just goes up here, or even above amplitude.
Well, no. It needs to occur before the amplitude computation. Yes.
I do like that. I do like a line that's small.
All right, so you can get rid of that long line because it's now deprecated. The velocity.to line we have already fixed. We have already implemented that. And then we have this whole peak time and bounce time 2 situation going on. That is all to compute the time of the next bounce. In other words, we want to update the bounce time seconds variable.
Right.
Right? So we will have a line that reads like bounce time seconds, and we want to update that so that the next time the loop goes around, the bounce time in samples will be, the bounce time in seconds will be correct. And maybe let's not use the peak time right now. Let's just inline that for a moment.
Sure.
How about that? To make our lives easier, so we have a single line to work with, or I don't know. It doesn't matter. We can do it with peak time. So we can compute the peak time, and then it is the velocity, blah blah blah. Except that it's not velocity initial.
It's
right?
just velocity now. Yeah.
Velocity now.
So I'm even gonna modify this right here.
And then you don't need the .2 in the name of the peak time variable. There you go. And then the bounce time in seconds is just 2 times the peak time. Well, there is an issue here, I think. The issue is the peak time is not taking in consideration our current time. Yeah, what we want, so this peak time is being computed using this formula above, right? We massage this formula to get a formula for the peak time. Am I right? So this formula is not taking in consideration the initial time that you are working with. It considers that the initial time is 0, but in our case, the initial time is not 0. The initial time is bounce time in seconds. So we should be adding to the initial time in seconds 2 times the peak time. I think that's what we want to do.
Yeah, so to calculate, this we calculate, then down here we add to it a bounce time seconds. Or sorry, bounce, yeah.
Yeah, or you can do it like what I did, which is the cute short way of doing it.
I do be liking that. Shibloinks, cool. So the bounce time increases by twice the amount of peak time, which we just calculated. And again, these could go. Can these go before the storage as well? So we do all the calc and then do all the storing?
We can. Yes, we can, because we are doing a very cute trick here, and it's a very subtle point that makes everything just work. The subtle point is, look at the bounce time in samples.
Yeah.
That's the one that we are using the previous bounce time to compute, right? So our lines here of the bounce time seconds update cannot go before that line. But the cute thing that we are doing that will make everything work is that we are storing that bounce time in seconds as the bounce time in samples. We are storing that information. So we can do the whole thing in one pass. If you want, you can move those lines above. Yes, you can move the peak time and the bounce time in seconds right below like the bounce time in samples or below the velocity, however you want to reason about this.
Below the velocity. Wait, did you say below the velocity or below this line, right?
Well, actually, you can move these two lines to whatever you want after bounce time in samples. Whatever you think that makes more sense, put it there. It doesn't matter. All the variables are independent.
I'm going to do this. That feels like good to me.
Yeah, and I appreciate this separation as well. It's something that I try to do in my code. All the computation, all the storage. And in some cases it pans out, in some cases it doesn't, but... Yeah, so now we have a big array filled with data structures with times and amplitudes. We have the cake, it's decorated. We had the recipe for the cake in the init block. Then we created some cakes in the init block. Then we are decorating the cake. Now we are ready to eat this damn cake. Jump to the sample block, and what we want to do is a loop very similar to the loop that we are doing in all other places with tap.index, blah, 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 blah. The structure of the loop is going to be the same. We're going to loop over all the taps in the array.
So first, I'm going to get rid of these lines because they're a repeat. Correct. And I am going to also just see, well, this needs to be amplitude. Bounce times samples needs to be bounce times samples. So this we're just doing to create the multi-channel thing. Then we need another loop to actually output this stuff, right?
Yes.
And that loop goes above.
It's a loop within a loop.
Oh, it's within.
Well, I want to do this. It doesn't matter, actually, because we have two independent things. One is the taps and one is the samples.
Yeah.
The channels. So they're independent. You can do this in whatever order makes more sense to you. For me, it usually makes more sense in one particular way, and that's usually how I do it. But I'm not going to say which way it is. Which way makes more sense to you? Do you want to loop over the channels first and the taps second, or do you want to loop over the taps first and the
channels second? To me, it feels like, well, you first create the taps and then you send them out. So to me, it makes sense if we do the taps and then send them to channels. Is that how you also think?
No, I usually think in terms of channels. So I usually think of what I want to do. I want to tap into this delay line 500 times. Okay, I'm going to tap into the delay line 500 times. Oh, I want to do that for the left channel, for the right channel, for the 25th channel. So I do the loop for the channels out, and then I do the loops for the taps
inside.
in. But as I said, they are interchangeable. They are independent.
Cool.
So it doesn't matter.
I do like the inside idea mostly because I can't wrap my head around it. Let's do the inside idea. Okay.
Okay. One advantage of this approach is that if you want to start prototyping something with mono, then you can more or less straightforwardly turn that into multi-channel just by wrapping everything with a loop and putting all the indices in the right place.
You mean the benefit to doing it like as two separate loops is this?
No. Two separate loops are necessary. It's just that the order I proposed with the outer loop being the channels and the inner loop being the taps is that if you just do the inner loop with the taps for a single channel, you can prototype the thing that way, and then you can wrap your whole program with another loop for the channels, and then you have multi-channel.
Scores.
So you already have the outer loop. All you need is the inner loop with the same structure we have everywhere else, where it says tap.index, blah, blah, blah. You just copy that loop structure inside.
Cool, and that needs to go... Where does it need to go? No, it can't go at the end because we haven't calculated this, so this needs access to that. Oh, wait, well, it has access to the slider block. Yeah, where does this need to go? Can it go just to the first line?
It can, yes, it doesn't matter. It depends on how you want to reason about this. Do you want to push stuff into the delay line first and then tap into the delay line? Or do you want to tap into the delay line and then push? This is going to affect one sample. It's going to be different by one sample, so it does not really matter.
Okay, yeah, let's tap into the delay, then push. So that means it goes above.
Yes, I would put it after the line that reads the delay line, blah, 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 because it's getting a hold of the delay line. Cool. So that's kind of cool. We want that.
And then just splap all of this stuff.
And then you can remove from the body of this loop, remove all the stuff that is computing taps. So you can remove from, I guess we do want to get a hold of the tap, so you can leave that line that you have your cursor on, because we want the tap. So you can leave that line, but then later it's all just computing stuff, and then we can remove
all of that. And I feel like in this case, I just want this on the same line so that it looks a little neater. Because, yeah, by this time, we now have these values. So we are... So do we even need to say this bit? Because we already stored the things. Yeah.
No. Yeah, you can remove those lines
the whole line?
Yeah.
Well, would you look at that? And
then, now you have everything you need. You have a delay line with samples from the past. You have information about the tap, the amplitude, and the time. So all you have to do is mix in with the current samples. So take those lines that read SPL, channel, blah, 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 to the end.
Take them to the end? They're already at the end.
No, I mean, take the 3 lines from SPL channel until the end of that statement, which is 3 lines from that. Yes, take all of this cut, remove it from there, and paste it after the line that reads tab equals blah, blah, blah.
Oh, sorry, I need to keep the semicolon there. Zoops. And make this a little neater. like this. Like this. In fact, I'm going to do it like this. And one of these, right, is needed.
I think so. I don't know. I'm getting confused with the syntax. But let's look at the line again. So sample at channel, that seems correct, plus equals the amplitude. Well, this amplitude variable is coming from the tap. So we need to say
tap
at
amplitude.
Tap structure amplitude.
Tap struct amplitude. Oh, and it doubled it up. Well, I guess that's on me. Tap at tap struct amplitude. Close this times. And then this needs to be tap struct time, right?
That needs to be the time, yes.
And a little boop, 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 boop.
And you know what? Put a semicolon there and remove everything after this, because everything after this is wrong. It was just the second copy, I think. Yeah, and now we need to reason about this parenthesis because I'm pretty confident there is some mistake there. For one thing, this push line does not belong in the inner loop. So put a new line there, right where your cursor is. And no, okay, I see the issue. Yeah, I think that we have one more parenthesis than we need. I don't know. Can you fix the indentation of the line that reads cyclobuffer.push? Because that's getting me confused. The indentation should be
one
to the
more
left.
back, like this.
Even one more,
like that.
This line is occurring at the same level as the outer loop. There you go. Yeah, that line. And then I am not sure that everything is correct, but can you save? If it compiles, then it's correct. Okay, so we have the ping pong thing on your voice. And it is working, by the way.
Hello? Is it still on my voice?
Hello, you're back.
Okay, cool.
No, it's fine.
All right, so let's try.
Yeah, something crazy happened. Mute everything, Arya.
Wait, is it still? Is there still sound somewhere?
Okay, I hear you again now, and I don't hear the craziness, but some crazy shit happened.
That is weird.
Yeah, let's get everything back under control. Make sure that everything is muted. Let's run one sound that we know what it is, the ball dropping. Let's hear that once. Not here. Let's see. Let's see everything.
I'm gonna mute this. Oh, sorry, I bypassed this. No, that is still doing that thing. Sorry, I'm muting this. Let's revisit the code.
Yeah, and it's very rare that these things work first time, right?
I guess that's what I'll say in court when Days sues me. Sorry, Days, your ears got shot.
Well, can you like do a full compile reset, save this and remove it from all tracks and just like drop it fresh on the track? Because I think I saw the elasticity equals to 1 in a slider, and the elasticity equals to 1 means infinite tapping and infinite feedback, and we don't want that.
We'll fix the mic in a second. Don't worry about that, because I also felt like maybe I accidentally put the ball drop delay on my voice, but I had not done that. And similarly, I had not, and this just goes straight to my black hole, and doesn't go through the master send. So that's weird that anything happened there. And now we don't have a ball drop on any of these tracks. This is just a keyboard track. These don't have any plugins on them. In fact, I'll disable the master send on this for a second, even though it's none of our concern. I will even grab all of this and disable the inputs to all of them. Now I will grab my ball drop. Oh, and we even have a hotkey for this, Option and F6. Puts the ball drop delay over here. And now that we have done all of that with the master channel still muted, and in fact, even though I just confirmed that this doesn't do anything, I'll still do that. And let's it's very slow. I can tell when I press space it takes a while to play. Yeah,
I see some taps happening, and I see the CPU is not happy, is it?
89%.
Yeah, so maybe a delay with 500 taps is not so cheap.
Let's just bring that down. Yeah.
You live, you learn.
No problem.
And also, I must admit that my library is designed to allow for the kind of flexible code that we are writing, when you can just change the number of taps changing a single number. But that is not optimized for speed. All this memory management that we are doing takes a lot of time and takes some resources, and it's not free. So if you look at similar effects in other libraries, if they want to have 50 taps, they have some block of code that they copy and paste 50 times and they change it slightly. There are even people who develop languages that compile into JSFX to try to reduce that repetition. And that is the fastest way of going about this. So one of the goals of my library is to allow for this kind of flexible code that we are writing. But it's still an experiment. It may or may not lie. For everything I did up to this point, I was able to get reasonable performance, but we'll see. Cool. It's still up in the air.
Well, for now, let's go down to, even 50 is too much. Why don't we go down to 30, let's say, of these.
Okay.
That's one thing, but also I guess we should check over here. Bounce time sample seems reasonable. Delay line seems reasonable. These tap values aren't sounds. These are places in the sample, correct?
They are places in memory. They are completely meaningless.
This dB minimum, I guess these are from your library.
Yeah, when you see underscores, you can ignore. You can pretend that my code is right.
So I don't see another problem, do you?
No, it seems correct. So do a full compile reset, remove it from the track, drop it again on the track, just really want to make sure that the thing is reset and we can see it. And if the CPU is okay, we can even maybe try to hear it. Because if the CPU is not okay, it's going to drop samples on the floor and it's going to stutter. But if the CPU is happy, then we can try to hear it.
I see another issue here as well. Let me quickly address that. I'm gonna mute this. Yeah, you see it keeps racking up. So at the beginning it seemed like it's functioning correctly, but now it just seems like it's keep adding stuff to itself.
Yes. So there are two things that I think of about this. The first is we may be going over 20 seconds. If the ball dropping it takes too long, then we go over 20 seconds and then all bets
I think
are off,
not. You know
because if we go
why?
over 20 seconds, we don't have
I
those
think
samples.
it's one of those things where it's like if you have to go 10 meters and each time your step is half the size. So because the time keeps getting so much shorter and shorter, like our first one is a second and then it keeps getting shorter. So I think at least by 50 taps we won't get to 20 seconds is my feeling.
That's a fair point. They are going to eventually tap out.
Yay!
Hey! Uh, so my other guess is that what we are doing is we are always adding to the samples.
Correct.
But that is going to increase the levels. So one thing that we could try is to average everything at the end, right? But I'm not too sure that this is the problem, because it would explain an increase in level. It would not explain. So the level would be louder, but it wouldn't increase.
Yeah,
It
what if
wouldn't
we
go up.
also change the sound decay amount back to we did 20. 20 seems like very low, but why don't we try that for a sec? So I'm gonna
Okay.
try full recompile and reset, remove, add again, and make sure everything is muted. It is on three stages of mute between this sound and the users and Shabloinks. Well, now we just heard it once. Oh, because it's bypassed, because I'm dumb. One more time. And even at the beginning this clip, so I'm gonna also bring this down a little bit. There we go. That looks.
Oh, it seems like people cannot hear
Cannot
you,
hear me
Arya.
at all. Not even.
Yeah. On the stream, I can hear you, but people on the stream cannot.
I shall fix. That looks correct. It's weird that y'all don't hear me. Y'all should be hearing me. Do you hear me now? Hello, everybody. Do you hear me now? No, I don't want to play that. There seems to be. Okay, Leandro, you can hear me. I'm just gonna say. Yeah,
I
I'm just
continue to
gonna say
hear
one
you.
more. I think another thing happened, and that is we crashed my black hole. So now none of the sound is going.
Okay, so
yeah, none of this.
okay, for everyone on the stream who cannot hear Arya, what is probably happening is that Black Hole, the application that routes audio from his microphone to the stream, not to Skype, it seems like Black Hole is not working right now. So Arya, can you please run this command? It is going to restart core audio for you, which will restart. Okay, so don't do that. It seems like people can hear you, but the microphone is very low in gain. And I don't get that because on Skype it normalizes the volume
Well, if you
anyway.
hear me too quietly for a second, be okay with that. I would say all of y'all. We do hear, but the mic is really low. Yeah, live with that for a second. But I just turned myself up. Hello, ASMR. How you doing? Forget about it, huh? Is this better? Ooh, forget about it. Yes, I do have my master muted. If you hear me, if I'm alive and indeed exist, but I am not going to the master with my voiceover. I'm going directly to my hardware output, which is the black hole. However, I currently have that muted because just looking at my meters, I feel like Black Hole has completely crashed and there's still some sound in it that does not belong to moi. So that's what's happening. But let me know if this seems pretty loud. I mean, this seems tolerable. I know it's not like optimum level, but for the purposes of knowing what the hell is going on, this should be okay. So let me know in the comments. I just said a lot of stuff. I probably could have heard a lot. I could have probably said a lot less. So Leandro, should I run that code now?
Okay. No, I don't think so. I mean, the command that I pasted, not a good idea because it seems like Black Hole is working. Right. Okay.
No, sorry. Black Hole is still not working. I am just going directly through OBS from my audio interface. The Black Hole. Yeah.
Oh, I see. Oh, yeah. To restart Black Hole, it's not going to only restart Black Hole. It's going to restart everything in Core Audio. So for sure, no one will hear anything, not including me, in the stream for a while, I think. But you can try it.
I'm going to say, hopefully people can hear me decently right now. I'm not going to get into resetting Black Hole because that would require closing ReaFIR. We might as well just end the stream.
No. Oh, yeah? You don't need to close ReaFIR.
Can handle it?
Yeah.
But it'd be weird to eat a mic the whole stream. Okay, how about I do that then? How about I run this action? Or why don't I kill the thing?
Yeah, we can try. It's a fun experiment. And if people can hear me, there is something that I want to say in reaction to what we are getting on the chat, which is like, so I understand why people were using ReaFIR and JS plugins to maintain performance. I really had some issues with that before using FL Studio. And yeah, so there is a trade-off in place here with the way that my library is doing things. And the trade-off is you get some flexibility at the cost of some performance. Now, the experiment and the reason why I want to build this library is because I believe that you can go very far before the CPU becomes a real issue that is unsurmountable, and you do have to give up completely in terms of performance and flexibility. You have to go all the way into the traditional way of doing things, which is like copy and pasting a lot of code. And even in this experiment that we are doing now, we have 30 tabs, and the CPU seems to be okay. It's like at 10% or something, 2%. I forget what I was looking at before.
I would also add,
it's like, 3%.
A lot of this performance issues is not even related to this, because I got 2 screens and I got 8 gigabytes of RAM and I got like sometimes 2 instances of ReaFIR open, and my computer is just like pushed to its limit while I stream. If I wasn't streaming, I bet even the 500 would totally be okay to run. So
yeah, and yes, and that is true. And there are ways to optimize the library so that it's doing less work and still keep some of the flexibility. It's always a trade-off. The more flexibility and correctness and security you have, the slower it's going to go. But there is a sweet spot, I think, that gives you very good performance and at the same time very good developer experience. That's what I'm trying to go for. If everything fails, then I will go to one of those other options, like a language that compiles to JSFX situation can be a solution that will be guaranteed to be as fast as possible and at the same time be relatively flexible. But we'll see. I will continue this experiment and push it as far as I can. Right, so it seems like you restarted Core Audio.
Yet. Before I press enter, I just wanted to tell everybody you will definitely stop hearing everything, right, Leandro?
I think that people will stop hearing you, that's for sure. But I don't know what's the routing situation between NDI, and then I don't know if it goes through Core Audio. I think it does. I'm not so sure. People may still be able to hear me. In fact, that's a good thing to test. So go ahead, hit the button, and I'll continue speaking. And if people can continue hearing me, then it means that NDI is not going through Core Audio, which would be kind of cool. And I guess it would kind of make sense.
2,
Yeah, go
1,
ahead. Hit the button.
Oops. Oh, it needs my password.
Yeah, and thing. So now, people, if you can hear me now, it means that NDI does not go through core audio, which is like remarkable and kind of cool.
I
So,
personally
do you hear me?
stopped hearing
Let me
you
know.
for a second,
And Aria,
and
are you
then
back?
I started hearing you again.
Yeah, Aria
I'm
is
not
definitely
back.
not back.
Am
And
I alive or am I dead?
that's weird because usually all the applications just pick this up without having to do any extra work.
Hello, how about now? Do you hear me? Let's do something risky.
And the other cool thing is that this just may be the way that this stream ends, with
Do you hear me
everything
now,
silent.
Leandro? You don't hear me. Shoop-doopsie-doopsie-doop.
Oh, you can hear me. Great. Fun stuff. So, NDI... Oh.
Can you hear me,
So,
Leandro?
the stream can hear everyone. I cannot.
Hello, hello. How are you? Won't you tell me your name? Hello. How are you? Won't you tell me your name? What you gonna do with all that junk? How about now? Do you still not hear me, Leandro? Leandro doesn't hear me. I don't think so. I don't think Leandro hears me, but let me know, chat, if you hear me, 'cause I think the chat hears me now. Nope, Leandro does not hear me. Interesting. So Skype really fucked up. You don't...
And Vaso is saying, whoa, that many hardware inputs. I have plenty of hardware inputs, like 5 of them. Just black holes, not let alone the audio interfaces and everything.
Can I do a regular check, like Command F in ReaFIR's IDE? Yes, you can. So... So yeah, I think it's Skype that's fucking up everybody. Like, everything else is up and running, but Skype is yeeting out of there. Yeet. Hey yo, Joey, forget about it. Is my voice also like good? Yeah, I'm going to restart Skype, so we may lose Leandro for a second. Or again, we'll definitely lose Leandro in a second. So Leandro is gone for a second, yo. He'll be back. Let me know if my voice, which is now coming back through Black Hole, if it's of a good quality and it's not weird. And I'm just gonna call Leandro again. There we go. Now you hear me, yes?
No.
What? What the fuck? He still doesn't hear me, y'all, even though nothing has changed, right? So that leads me to the conclusion. That leads me to a conclusion that I think is correct. So first of all, Leandro, now you hear me, right?
I do.
So my conclusion is that I was sending you my voice through VB cable. So I have come to the conclusion that VB cable now crashed. So I'm just temporarily sending myself to you through the old interface. So probably a little quieter than it's been up to this point. And here's my screen. And I think we are now ready to resume proceedings.
Yes. And like, your voice is fine, maybe too high, Ru said, but...
Maybe too high.
I mean, let's just give this a try, and if there is like a low-hanging fruit that we can try to fix, we will, but otherwise we can wrap this up, right?
Sure, yeah, I gotta leave soon either way. So one more time, I'm gonna make sure everything is muted. Let's see this. Okay, that looks to be at a listenable level. Do y'all want to hear it?
Yeah.
All right. Okay, so definitely sounds like a ping pong ball. And
it does. I don't know. I am receiving the audio from your audio interface. I don't hear any of that. I have to trust your ears.
Damn.
Does it sound okay?
It sounds nice. Actually, I'm getting a little cocky here. I'm gonna change this number to 10. Okay, and do a full recompile reset. I'm going to mute my master again. I'm going to remove this, and I'm going to reinsert this, and oh, now that sounds like something I'd be excited to hear. Here, Leandro, I'm not gonna leave you hanging. I'm gonna do something for you.
And my Skype is doubled for the stream, so if you can do something about that.
Oh, what the shit? How can that even be? I like that we didn't change anything in Skype, and Skype is almost like jealous. It's like, no, pay attention to me. I wanna fucking be annoying. It's like, bro,
I'll try to be quiet as to not annoy the stream.
Hold on, I want to give Leandro the good experience, y'all. So I'm going to try something very simple and very quick, and that is to go black hole 5 and hit OK, and I'm going to go to my advanced audio properties. Now this is something where I'll forget that I've done and lose my mind. Leandro, hello, you hear us?
Yes, I do hear you.
Okay, so now you're gonna hear everything, hopefully. Let me know if you do. Just to...
And it seems like the stream also doesn't hear the effects, but I don't know.
The stream should really hear the effect, otherwise, like, the meters in front of me are lying to me, because, look everybody, this is the stream. Y'all should be hearing all of this. If you don't, I don't know what to do. So anyway, so Leandro, let's test this one more time. We see that the sound is at a reasonable, listen-toable rate. So we're testing. It really sounds like a ping pong.
I didn't hear that. That is a bummer.
That is a bummer.
That is anticlimactic, but it seems like it's sounding like a ping pong ball.
Oh yeah, it's sounding good. I really want you to hear that.
Oh yeah, it is sounding like a ping pong ball. It may probably need to be louder.
Yeah, so you did hear that this time, and the stream heard that this time.
I heard that, yes. That was great. I'm very happy.
Yeah.
And in fact, let's increase the level on this and hear it again. And I want you to like render this and let's put it next to the other one to see. I mean, if we got the height wrong, I think that the result of that is just we need to time stretch it, but then it should match.
I actually heard something right away that didn't make sense, which was some triplitation. But yes, I like where your mind is at. So one more time, I'm muting the master just to do a preliminary check. You see how they're like, I guess you don't see with the resolution that I do, but they're a bit like clustered up. So that's interesting. But anywhoozles, let's have everybody hear this and record it. Oh, I see what's going on.
Yes, Arya, I do not hear you.
They just went and took her jobs,
Now I hear
Now
you,
you hear
Arya.
me. Okay, so something with my main black hole is fucking up. But Leandro, we recorded this. I can send it to you, but I know what the problem is with
What is the
with
problem?
what we've done, and hopefully everybody else hears us. But this is a good time to wrap this up. Either way, the problem is that now the bounces 1, 2, and let's say 3 are going into our buffer. But then the bounce 4 is not independent from those. The bounce 4 is taking the sound from all those buffers and repeating them again. Whereas, just as an example, in ReaDelay, the thing I was doing.
Oh, yeah, right. So the issue is super simple. Fix it. It's super simple. Remember how I said that you can do the pushing of the sample into the circular buffer either after or before? I was wrong because we are changing the sample. So what we are doing right now is kind of a feedback thing.
Yeah.
That's not what we want.
No.
Instead, just switch that line to be above and everything should be fixed.
Which is which line? It's
the circular buffer push needs to occur right after delay line equals something something.
I see. And then so get as well, no?
No. Just this last line.
Cut it.
Just this last line that is pushing. Cut that. Put it after delay line equals that there. Yeah. Right? Because we are pushing a sample into the circular buffer, we better do it with the original sample, not the one that we just mucked with. So save that and let's try this again. This is going to work and we're going to have a great finale.
Okay, grand finale. Let us know, people, if you hear us. Everything seems to be crazy. I actually know for a fact that nobody will hear what's about to happen except for me. So not a very grand finale, actually. Because my black hole seems to just be not pushing out the correct sounds, is the way I would describe that. One more time like this, one more time like this. I'm gonna check something one more time, even though it's probably fine. Do 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 dee dee doo doo dee doo boo doo boo 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 boo. No, yeah, it's fine. I mean, why wouldn't it be fine? It's been the exact same way.
Yeah, I just wanted to check because it's hard.
Yeah.
Streaming can be hard sometimes.
So I'll show everybody something just so that we're all on the same page. You see on my black hole, I'm gonna not say anything. You see how it's going tap, 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 tap. Without hearing it, because I don't hear that. Only y'all do. I feel like that's a bunch of clicks, and that happens when black hole crashes. And it seems like black hole just crashed again.
Yeah.
So nobody but me will actually be able to hear what's about to happen. So if it's correct, what's about to happen, then I will print it and I will add it as a media source to my OBS so everybody can hear it.
Sounds complicated.
We'll just call it a day. Yeah. All right, here we go. Everything is muted. Okay, well, that looks correct, though it died kind of too soon, but let's listen. Let's Arya hear it. Oh, but that is fucking ping-pongy as shit right there. Why are you not picking up stuff? Did I fuck it up?
And here's the guy who is trying to teach people how to use ReaFIR on the internet.
Here we go. This is ping pong folder. I mean, no, I'm convinced that I'm doing everything correctly. There we go. I literally didn't do anything.
Constant. The constant is What didn't do anything?
I didn't change anything the first time, and the second time I recorded it, but the second time it recorded. So I was
Oh, but
totally...
change that constant. I think that we are decaying too fast.
We set it to 20, then I set it
10?
to, now it's set to 5. Let's set this to
Yeah,
2. Save
yeah.
this. I'm not even going to recompile. I'm going to get cocky. The downfall of many, many people. Still decays pretty fast, but that looks like a motherfucking ping pong, doesn't it?
Yeah,
All right.
Look at that decay. I mean, if you see the shape of the wave and the spacing, it's definitely exponential. Can you put that next to the real ping pong ball?
And don't worry, I'll make sure y'all hear this. So if I do this, and then I just stretch this until the second one lines up, more or less. I mean, this looks pretty nice. Of course, our heights are wrong and stuff, but this looks like a thing.
Yes, and we do have like the bounciness of the ball that we need to modify, right? It's
Right.
just a slider. To get this right, we need the right bounciness, we need the right elasticity, we need the right height. So of course it's not gonna line up perfectly, but it's not too bad.
Sorry, Bob. I'm gonna put this into my OBS in the dumbest way that I never thought I would have to do, and then we will call this a die. I'm gonna import this audio file to my thing. I hate having my Finder in view because I'm like, what if somebody sees something they're not supposed to? But then I'm like, I don't have anything you're not supposed to see. Mostly my... But I don't know. At any point, it's like, oh, this secret project for me to assassinate Justin Trudeau may show up. And then what are you going to do? Here we go. Print-20. Print-20. Cool. I love that. I love that I'm just at the same place and not seeing the same stuff. That's just beauty. Like, I'm in the same directory and the same stuff doesn't exist here. Like a print-20. That's I mean, that's the icing on the craziest cake I've ever seen in my life. I'll bring it over so y'all don't think that I'm crazy. Well, I'm definitely crazy. I am crazy. There you go. I brought it over, and it's always the fault of humans. There we go. Print-20. There it is. Okay, here we go. Are you ready for it, everybody? I'm just going to loop it for a while. Hit OK. That's it.
Of course, I don't hear that because I am hearing it via Skype.
But that's what it is, everybody. Things are really falling apart. So let's call it at this one. What can I say? My computer can't handle my ambitions. So please donate to me so I can buy another computer. Hey. And thanks, Leandro, for being with us. All this stuff is fun. I mean, even when shit starts to fall apart, sounds like a good time to me. So I hope other people agree. Black hole collapsed. Oh, shit. Get it? I get it. That one looks like a real digital delay. That sounds great. Cool. I'm glad you liked it, Daysru. Thank you, Leandro, as always, for... I think we have fun together over here.
Yes.
So
I'm looking forward to doing the graphical user interface for this one. That is going to be a lot of physics and math.
I guess a couple of things that I got to do. I'll do a measured bounce, meaning I will take note of the material, the distance of the droppage, and I'll make sure it's on like a flat surface. I'll record it with a decent mic. Not that this is not a decent mic, but like I'll use a Foley mic.
Yeah. So can I ask you to do one more thing when you're doing that? Can you like put a measuring tape beside the thing. You need to do
Yeah,
that
that's
to
what I was
measure
gonna do.
the
Yeah.
height where you're going to drop it. But record it with a camera so that we can see the height of the second bounce, and that is going to help us determine the
Cool.
elasticity.
I wish I had a camera that could
And
do
then with
slow
that,
motion.
oh, probably your phone can do that. And then we can put to bed the idea of whether we want the air resistance or not on this thing.
Fantastic. Okay, I actually think that I may be able to. The problem with me is that I need to remember this, but if I remember to, I may be able to get a slow-mo camera. So, because I work at TV now, so they're going to have something. Cool.
Great. All right. So I think that's it for now. Thank you very much for having me. And the schedule is that tomorrow I'll be working on this library that we're working together. You are using it. I am working on it. And we'll be talking about Fourier transforms. On Wednesday, we'll be together again, and I will be mixing some drums, probably. Am I right? Okay.
Wait,
So,
mixing
yeah.
some drums, or are you mixing the stream is about to start? You're mixing that. Okay.
Yeah, we'll mix the drums
Cool.
in that, I think. You asked me to print the drums, so I think that we are going to mix it.
And then, so I guess, as like now as the author of the library, did you like find some stuff that you're like, oh, I need to change this, or?
We may go with simpler data structures that are not as powerful, but that may be faster, because 50 taps, 2.3% CPU, not the best, but in
Cool.
any case, we'll see.
Well, I unfortunately won't be able to join you, but I always watch them in post. I just can't ask questions. So that kind of sucks for me. But everybody else, highly recommend you join these streams. Subscribe to Leandro. His info is in the link below. Take care of yourselves. Next Monday, we may have a special guest on the stream, which I won't say until it's confirmed. When it's confirmed, I'll make a thumbnail and put the face of said person there. Yeah. Take care, everybody. I'm signing off. Goodbye. Bye-bye. Okay, I think